So let me grab this. All right, so let's see, we're in 13.8, and we're doing part 2. And I want to start out with a question. So looking at this, this is what I have here is the graph of the level curves of a surface. And we want to figure out A, B, C, and D. What kind of points are they? Could they be maximums, minimums, or saddle points? So these are our level curves. So we're looking at a contour map of this surface. What would A be? Or what could A be? Could be a maximum or a minimum. So we have this point, we have our level curves around, so this could be the top of the hill or the bottom of the hole. How about B? Maximum or minimum? And how about C? Saddle point. So, and how about D? Saddle point. Why looking at this graph, why couldn't C or D be a maximum or minimum? Why couldn't these be at the top of the hill or the bottom of the hill? Well, what does this line tell us? It's a constant. So the altitude is constant here. So if I go from here to here or here to here, the z value is the same. So that doesn't, unless the top of the hill is really flat. And what made us pick out A and B as a maximum or minimum? The lines and how close they were to get. The level curves, what I think of as the level curves are kind of, they're closed curves around the shape. So as we go from here to here, we're changing elevation. As we're going from here to here, we're at the same elevation, if we're thinking of it in those terms. So these, if they were maximum or minimum, they'd have some kind of closed curve. Or if they, I guess if you had like a long narrow ridge, you would have level curves. So if we had C and D on a ridge, is what I'm thinking, you would have level curves that went kind of parallel to the ridge along like that, and then eventually these would curve around somehow and meet up somewhere. But if you had a ridge, you'd have level curves that were kind of parallel to the ridge as you went down, or if you were at the bottom of the valley, they would go up or down. So the meeting, these two meeting is also a clue that we were talking about the saddle point. So I just wanted to talk about that in terms of visualizing surfaces. I always like to be able to have some kind of idea about what we're talking about. All right. Absolute extrema. We said yesterday that if we're looking for relative maximum or minimum, that we set our first partials equal to 0. We find where they're equal to 0 simultaneously, and then we run our second partials test to decide if we have a maximum, a minimum, or saddle point. And we said that we started off by saying that our function attains an absolute maximum or minimum on a closed bounded region. And we said also that our maximum or minimum is going to occur at a critical point, or if we have a bounded region, our maximum or minimum could occur on the boundary. Now the single variable function, it's kind of easy because our boundary is just a point at either end. For a multivariable function, our boundary can be any kind of curve. So that's what makes absolute maximum minimum a little more complicated. So when we're looking for an absolute extrema, what we're going to do is we're going to have a bounded region. So absolute extrema, we're talking about a bounded region. We're going to have some kind of boundary. So our steps, we're going to, we have to find the critical points inside the region. So that's, we're using the tools that we talked about yesterday. Set our first partials equal to 0 and run our second partials test. Then we have to, since we have a bounded region, we have to check our boundary. Like we have to check our endpoints of a single variable function. So we're going to find the extreme values on the boundary. Now on the boundary, we're going to have some curve that gives us our boundary curve, and what we're going to do is use that curve to simplify our expression for our function, and then we use tools that we already have for finding extreme values. So we're going to take the derivative, set it equal to 0, essentially. And then we find our critical points. We find our what I didn't write here, we find the value, our function value at the critical points. Because our maximum or minimum is going to occur at a critical point or on the boundary. So we find our function value at the critical point. We find the extreme values on the boundary, so we're finding the extreme value of the function on the boundary. The maximum, the largest value is going to be our absolute maximum. And the smallest value is our absolute minimum. And we're talking about the absolute maximum or absolute minimum in that region. So in that region, that's going to be the absolute maximum or absolute minimum. So all we're really doing today, what we're doing is the step 1 is what we practiced doing yesterday, finding the critical points in the region and finding the function values at the critical points. So we don't even have to run the second partials test on the interior of the region. We just find the critical points and find the function value there. Then we're going to find the extreme values on the boundary, and we'll talk about how we do that when we do a couple of examples. The largest function value is our absolute maximum on that region. The smallest value is the absolute minimum on that region. All right, so let's take a look at a couple of examples of going through this procedure. The procedure not necessarily difficult, but there is some work involved. Okay, so here is our first example. We have f of xy is 2x minus y squared. And our region is the region in the xy plane. For this one we get points. 2, 0, 0, 1, and 1, 2. So we have this function. We're going to have this surface above a triangle in the xy plane. Let's draw a sketch of our region. So here's our xy plane, and I'm going to go from the point here. We have a point at 0, 1. We have a point up here at 1, 2. And point over here, 2, 0. So there's my region. Something like that. So we have the surface above this region. So our boundary, the boundary of this region is going to be 3 different line segments. So we're going to have to find the maximum minimum value or the extreme values on 3 different line segments to test our boundary. Find our maximum minimum on the boundary. So let's find our critical points on the interior first. So we're going to find critical points. So we're going to take our first partials and set them equal to 0. So f sub x, our first partial with respect to x, is going to be, you get a 4 times 2x minus y. And f sub y, we get a minus 2 times 2x minus y. When we set both of these equal to 0, we solve this and we get y equals 2x. So inside the region, our critical points are on the line. They're all the points on y equals 2x, the line y equals 2x. So I'm going to substitute y equals 2x into my function. So if I substitute that into the function, so f of x comma 2x, what do I get there? If I substitute y equals 2x for my function value. 0. F of x 2x equals 0. So along that line, the function value is 0. So that gives us one possible absolute maximum or minimum. Could be along that line. Now we're going to do our second step. We're going to start finding the extreme values on the boundary. Well, our boundary is 3 different lines. So we have to find the extreme value of our function on 3 different lines. So we have to test between each set of points. So between 0, 1 and 2, 0, I'm going to find the equation of that line. We can find the equation of the line. We have y equals, if I find the equation of that line, y equals minus 1/2 x plus 1. So that's the equation of the line between those 2 points. And I'm going to substitute that into my function and find the extreme values on that line. So I'm going to substitute y equals negative 1/2 x plus 1. So f of xy on that line is going to be 2x minus negative 1/2 x plus 1 squared. And I can simplify that. If I simplify that, that simplifies to 5/2 x minus 1 squared. And I need to find the extreme values there. So to find the extreme values of a function that looks like this, I take the first derivative and set it equal to 0. So I get f prime is 5 times 5 halves x minus 1. The 2 cancels with the 2 in the denominator here, right? When this comes down, it cancels with that 2, and then get that to the first power. So when I take the derivative of the inside, I get just 5 halves, and that multiplies by the 2, and that's where I get my 5. Okay? And this equals 0 when x equals 2/5. So I plug that back into my function when I plug in x equals 2/5. I get f equals, when I solve for y, f equals f of 2/5 equals 0. But I have to also, on my boundary, where could the extreme values of the function occur on this segment? At the endpoints of that segment. So I have to test the endpoints of that segment. So at so this endpoint is when x equals 0. I get f equals 0 at that endpoint. And I need to test this boundary, f of 2, 0, of that segment, f of 2, 0. When I substitute that in, I get 16 if I evaluate my function at 2, 0. So my minimum is, so far, is 0, and my maximum is 16. Now I need to check another boundary. I have to do this 3 different times for each boundary. So let's check between 0, 1 and 1, 2.
Wait, why did we check 0?
We had x equals 0. Or sorry, did we? X equals 2/5. F of 2/5 equals 0. So we can check. So we need to check 0, 1. We didn't check 0, 1. F of 0, 1. If I plug in 0, 1 here, if x is 0 and y is 1, what do I get? F equals 1. Yes.
I'm also confused on what you mean by that.
Oh, so if I solve for, I should put my y value in here. So if I solve for y here, the function when x equals 2/5, the function value, that evaluates to 0. That's what I meant by that. All right, so let's find the on another boundary. So between the points 0, 1 and 1, 2. There I get y equals x plus 1. So f of xy on that boundary is 2x minus x plus 1 squared. And that simplifies to x minus 1 squared. And when we find the take the first derivative of this, f prime equals 0 when x equals 1. And when x equals 1, there, y equals 2. So f of 2, 1. Sorry, 1, 2, sorry. F of 1, 2. When x equals 1, y equals 2. F of 1, 2 equals 0. And then we want to check the other endpoint of that region. Well, the other endpoint is 0, 1. We already figured that out. F of 0, 1 equals 1. So far our minimum value is still 0, and our maximum value is 16 here at 2, 0. And then we have one last boundary to check here. So between between 1, 2 and 2, 0. The equation of line between those 2 points is y equals minus 2x plus 4. So my function there, my function of xy becomes 2x minus 2x plus 4, and we're squaring that whole quantity. And when I simplify that, I get 4x minus 4 squared. And this is going, if I take the first derivative, set it equal to 0, I see that, let's see, I get f prime is 2 times 4x minus 4 times 4 equals 0 when x equals 1. And when x equals 1, y equals 2. I'm plugging that back in here. Y equals 2. F of 1, 2. We've already checked that. Is 0. And we check the other endpoint. F of 2, 0. Checking the other endpoint of that region. F of 2, 0 is 16. And that's the same value that we got there. So our absolute maximum here is at 2, 0. At 2, 0. And f of 2, 0 we found out was 16. And our absolute minimum along the line y equals 2x, and we get f of x comma 2x equal to 0. And all of these points where we evaluated and we evaluated to 0, we were along the line y equals 2x. Except for here at f of 2/5. So our absolute maximum is 16. Our absolute minimum is 0 along the line when y equals 2x. So a fair amount of work to find an absolute maximum, absolute minimum, depending on our boundary. Here we had to do a fair amount of work because our boundary was 3 different line segments. So we had to find our extreme values on each of those segments of the boundary. So that involved setting the first derivative equal to 0 and testing the endpoints of each of those boundaries. So let's take a look at what this surface and what this boundary looks like here. So there's our triangle in the xy plane. I've got it turned around here a little bit. So we graphed it. So there we go. Is that how we graphed it? Or was it the other way? Is that something like that? So there's our region in the xy plane, and there's our surface on that region, and the line y equals 2x is along this minimum here, and then the maximum is up here at this boundary. So that's what we're looking at for that surface. And along the line y equals 2x, our function value is 0. All right, questions on our procedure there? So find our critical points on the interior by setting our first partials equal to 0. Find the function values at our critical points, and then we need to find the extreme values on the boundary. To find the extreme values on the boundary, we're back to using tools that we've used previously. Set the first derivative equal to 0, and in this case, because our boundaries were segments, then we needed to test the endpoints of those particular boundaries for the extreme value of the function on those particular on those endpoints. So each endpoint of each boundary segment. The smallest value is our absolute minimum. Largest value is the absolute maximum. All right, let's look at one more example. Not quite as involved this time. Just so we can see the procedure again. All right, so for this one, our function of xy is 3x squared plus 2y squared minus 4y. And R is our region of the xy plane. Bounded by y equals x squared and y equals 4. So in the xy plane, our region is going to be a parabola. So this one is a little easier to test, a little easier to find find the extreme values on our boundary. So we get a parabola like so, and then we get a line across there at y equals 4. And our points here at the endpoints on our boundary, this is going to be the point 2, 4. And this is going to be negative 2, 4. So we want to find the critical points on the interior. On our interior, we take our first partials, f sub x equals 6x, f sub y is 4y minus 4. And we get f sub x equals 0, nice and easy, when x equals 0. And f sub y equals 0 at y equals 1. So we plug that in at 0, 1, f of 0, 1, find our function value. Our function evaluates to negative 2. So that's one possible absolute maximum or absolute minimum, is f equals negative 2. So for our boundary, we only have two pieces to test now. We have the line y equals 4, and we have the parabola. So on y equals 4, we have f of xy. I'm just substituting y equals 4 in here. We have f of xy equals 3x squared plus 16. Substituting y in for 4. And x is between negative 2 and 2. So that's going to be our endpoints of our boundary there. And we're going to test, we're going to find the extreme values on that boundary. So we find f prime. F prime on the boundary is 6x. So equals 0 when x equals 0. And we're going to plug in on the boundary 0, 4. And we get f equals 16. So I'm just plugging 0, 4 into my function. And then we want to test the endpoints of our boundary. So if f of plus or minus 2, if x is plus or minus 2, 4, I'm going to plug those into my function and find what my function value is at those endpoints. That evaluates plus or minus 2, 4. I get 28. So far my minimum is -2 at the point 0, 1, and my maximum is 28 at plus or minus 2 or 4 at those 2 points. And then we need to test our other boundary on y equals x squared. Plug that into my function, f of xy is, this simplifies to 2x to the 4th minus x squared. Take my first derivative, f prime is 8x to the 3rd minus 2x. And just to simplify that, I'm going to write that as 2x times 4x squared minus 1. And this is going to be 0 when x equals 0. This part's not going to give us a 0 value. Oh no, I'm sorry, it will. This is going to give us 0 when and when from this piece, when 4x squared minus 1 equals 0, we get x equals plus or minus 1/2. So we get a 0 from here and a 0 from here. And we know that when x equals 0, our function, this function evaluates to 0 along that boundary. F of 0 is 0. And before that's when I said f of, what was it, 5/2. So I'm on the boundary, so I'm just evaluating the function. I'm evaluating this function at x equals 0. So f of 0 is going to give me, what do I get here? When x equals 0, f is 0. And when f is plus or minus 1/2, when x is plus or minus 1/2, f of plus or minus 1/2, I get negative 1/8. So our maximum value is 28. Our absolute maximum, f equals 28 at the points plus or minus 2, 4. And our absolute minimum is f is -2 at 0, 1. And then let's take a look at what this looks like. So here is our function. There's our parabola. And along the top there we have y equals 4. Turn it sideways there so we get our maximum values at those two endpoints of y equals 4 up here, and here. And our absolute minimum is at 0, 1, kind of down right in this area. It would be our absolute minimum. You can see how it kind of dips down there. All right. Questions on our process. So, depending on our region, these problems can involve a fair amount of work. We find the maximum minimum values on our interior by finding our critical points, setting our first partials equal to 0, and then we maximize, or we find the extreme values on the boundaries. So we're going to substitute our boundary conditions into our function, take the first derivative, set it equal to 0, find the function values at those critical points, and decide which one is the absolute maximum, which one is the absolute minimum. All right, homework. And then I want to do the number 47, I'm writing 47 twice, but I want you to do 47 the second time with our region r equals xy such that x squared plus y squared is less than or equal to 8. So you're using the same function for this. This time our region is this, the boundary is a circle. Oh, and I wanted to add a couple true or false questions to this. Number 55 through 58. All right.